Hi all, it's Dave Giles here, and welcome to the ninth lesson of Cambridge International IGCSE Physics P2 Thermal Physics. And today we're looking at thermal conduction. And I want to describe how conduction works in solids. So, start a little question here. Describe why wool is a good material for a coat. And two ways you could potentially answer that. Wool is a poor conductor, or wool is a good insulator. Now, to improve the answer, I might add the word thermal, just to be clear, we're not talking about electrical, but wool is a poor thermal conductor, or wool is a good thermal insulator. So this is how conduction works in solids. You've got a heat source here, and you've got some atoms. Now, we're looking here at a non-metal as the first example. So we're looking at a metal, but we're looking at just the atoms for now. So atoms are energized and vibrations increase because of the heat source here. Then this source here is heated, vibrates more, which causes the next one to vibrate, and it fans out until eventually the vibrations spread throughout the metal, leaving the whole rod energized. Sorry. You can see it here in this little animation I've got. Starts off this end, starting to give an energy. Then the energy is transferred down the line all the way to the end. That is how conduction works in any solid, but more specifically in metals, we have to look at something else, which is the free electrons. So we'll start off by looking at a non-metal, which is graphite. So heat one end of the graphite rod, and the heat energy travels to the other end. As you can see here. And one atom vibrating causes the next one to vibrate, etc. However, in a metal, such as copper, which is a good conductor of heat, if you heat one end of the copper rod and the heat energy travels to the other end, it happens a little bit quicker than in a non-metal. And that is because they've got free electrons. So if you do chemistry, you might have done metallic bonding, but basically in between atoms, you've got free electrons. And now these electrons are tiny by comparison to the atoms. So when they're given energy, their energy is transferred much quicker to the other end because they can move much easier. So you can see there, these atoms, go back a little bit, these start to vibrate much faster than in the metal. Now, just be clear, even in the metal, you will still get the atom vibrating as well, transferring heat, but the electrons will reach the other, will cause conduction first. So, some questions here for you to have a go at. Pause it and then give it a go. Okay, what is the opposite of a conductor? That would be an insulator. What happens to the energy of a solid when it is heated? The energy is increased. Why is this a good design for a pan? The metal, this bit here, where you put the food, is metal, which is a good conductor, so food heats up quickly. The handle is wood, which is a good insulator, which will prevent burns to hands. And describe why gas is a poor conductor. Now, gas particles are all spread out. This goes back to previous learning. And when one particle of a gas gains energy, it is not attached to another particle or atom to transfer the energy to. Okay, this is a paper 2 question, multiple choice. A bar of metal, which is a good thermal conductor, is heated at one end. What is the main method of transfer of thermal energy along the bar? The main method is the electron movement. So it's C. Question 6 here. One end of a copper bar is heated to a high temperature. Which mechanism is responsible for the transfer of thermal energy to the other end of the copper? It is, as I've got at the top, the lattice vibrations of the copper atom ions only. It's not that. We'll look at the bottom, the movement of high energy electrons along the bar. Yes, it is that, but it's not the only way. the movement of high energy copper ions along the bar. That is part of it, but not the whole thing. So it must be B, the lattice vibrations of copper ions and movement of high energy electrons along the bar. It is a mixture of both. So the answer is B. And C, sorry, it's number 7. Thermal energy is transferred by conduction in a metal bar. Which statement is not correct? So which is the false statement? We'll start from the beginning. Fast vibrating ions leave the surface. Well, we're not talking about heating up a liquid here. So yeah, it's that one, A. That is false. So we're going to have a look at some experiments to demonstrate thermal conduction. Now, one of them is here. So this is a thermal conductivity bar, and you place this in water. And when the metal gets hot, this changes color, this strip. So this was put in water, boiling water for say 10 seconds, and this is a picture taken after a certain period of time. So they've all received the same amount of heat energy because they're all placed in the water at the same time. And you can see from this, because the heat has rose up the copper first, or fastest rather, copper is the best conductor, then aluminium, because it's not quite as high, brass, the third conductor, and then steel is, by comparison, the other three, a poor thermal conductor because the heat has only traveled a little bit up the metal bar. Now, a common classroom practical you might do, and you might see this in paper 5 or paper 6 question, is having different metals heated by a source, and you should have it so they're all the same length, they're all the same thickness, etc. And you attach something to the bottom, something like drawing pins. In this example, it's a ball bearing, but normally it's drawing pins, and you attach it with something like wax or Vaseline. You heat it up, and when the wax melts, the pin drops. So you know the one where the pin dropped first was the best thermal conductor because the heat reached the end of the bar first. Now, conduction only happens in solids. Okay, and this can be proved by taking an ice cube and you have some sort of weight and you put it in the bottom of a boiling tube and you fill it up with water. When you heat up the boiling tube from the top, so you heat the top of the water, nothing below it receives much heat, so the ice cubes remain solid for quite a long time. It'll be different if I heat it from the bottom. That would be convection, but we'll look at that in the next lesson. Okay, so little question here. A student investigates the ability of water to conduct heat. She sets up the apparatus as shown. As shown, and heats the water strongly with a Bunsen burner. Okay, describe what she sees, or what she observes, sorry. The water at the open end of the boiling tube boils, but the ice cube does not melt. Explain why. Water is a poor conductor, and so thermal energy is not transferred to the ice cube. And how can wearing many thin layers of clothing help you keep warm on a cold day? This one's a little bit tricky. It's not related to this diagram. Air is trapped, and air is a bad conductor of thermal energy because you've got gaps between the clothes rather than one big thick layer of clothes, which is what this question is referring to. Okay, and a paper 2 exam question. The table shows materials and whether each one contains 3 electrons. Use the information in the table with comparison of the thermal conduction in the material is correct. So the best conductor is going to be the one which is a solid. Okay, so solid is good for conduction. So the answer is going to be, the best one will be R. And it's also got 3 electrons. That is the other main thing. We're looking for 3 electrons, so it's a metal. So the answer is C. And here is a past paper 6 question, a practical based question. I'll give you a minute to read it. Then we'll talk through it. Okay, so it's metal's heated. Here we've got rod and we've got some wax on the end with a marker, something on the end here. So one other piece of equipment is required to compare how quickly thermal energy is conducted near the piece of equipment. You're going to need some sort of timer or a stopwatch, and suggest three possible variables that a student should keep constant in order to make a fair comparison between the different materials. So they include the length of the rod, how thick it is, make sure you always put the same amount of wax on, make sure you use the same markers throughout. If one's heavier than the other, it'll make a difference. It's got the same different surface area. Make sure you give it the same amount of thermal energy. That's the main ones. Put a mark scheme on. Okay, so that's it. Thank you very much, everyone. The next lesson will be on convection. And again, I will post a link to that down below. Thank you very much.